Okay. So in today's meeting, right, we're going to look at okay, so we looked at the case where we just had some measure space. Um so so we have some measure space um x sigma mu, and then we looked at integrable functions. We looked at how to um integrate functions. Right? Very simply, we looked at simple functions, and then we looked at approximations of um, integrable functions by simple functions, and then we defined the integral in that sort of way. But this doesn't really help us with computations, right? Like, sure, for the theory, it's very strong. Like the dominated convergence theorem becomes very nice to prove. The monotone convergence theorem becomes very nice to prove. But how about actually computing integrals, right? And we're going to mainly focus on we're mainly going to focus on Rn, okay, with the Lebesgue measure, and I'll denote the Lebesgue measure on Rn like this. Okay. So we mainly worry about this. Yep. So let's look at a very simple example, right? Let's look at the integral over the unit square of the function 1. Okay. Now, this is a simple function, so it's just 1 times the measure um, of this interval, and then the answer is 1, right? But now imagine that this function was slightly more complicated. For example, what if we wanted to integrate the function, um, say we wanted to integrate f of x, y equals x squared plus y cubed, okay, over 1 squared. How about this? Now, it's not very easy to even come up with simple functions that would approximate this, right? So we have to do something else. So we would hope that an integral of this form over here would break into two integrals where we integrate over the x-axis and then we integrate over the y-axis. So what do I mean by this? So let me draw the square. Okay. So this is our square, 0, 1, 1. So one thing we could do is we could look at the function that takes some number x, right, and gives you the integral up to this point where this is x. Well, I guess it would be like this actually. So it assigns to you the integral with x fixed. Okay. So we fix x, right? And then we could take this function and then integrate it with like along y. Okay. So that's exactly what we're going to talk about today. So um we now look at how to decompose decompose an integral in higher dimension, like in now when I say the words higher dimension, take this with a grain of salt, but um higher dimension, I hope you at least have a geometric understanding of what higher dimension means. So like for example, the line is a lower dimension than the square in some sense, right? Into lower dimensional integrals. Okay. Into lower dimensional integrals. So what I mean by this is we would hope that the integral over the square of the function f of x y, well, f d lambda would equal the integral over one of the squares of the integral of one of the other squares of f x y, where now we fix x, right? Oh, sorry, we fix x, so we integrate with respect to y, um, and then we integrate that function with respect to x. Okay. So what I mean here is that this thing is integrate with respect to y, whatever that means, and then this means integrate with respect to x. Okay. Does does all of this make sense? Like, does the motivation for today's meeting make sense? Yep. Okay. So this is the main idea that we're going to try to grapple with today. Okay. So the way we're going to look at this is we're going to take two measure spaces and then we're going to ask ourselves, if we take the Cartesian product, can we define a measure on um like, is there a suitable way to define a measure on the product space? Okay. Because if we look at the square, we've decomposed the square into a Cartesian product of a line with another line, right? So the idea, start with measure spaces, start with measurable spaces. Um, x sigma x and y sigma y, and try to define a reasonable sigma algebra on x cross y. Okay. So that's the main idea that we're gonna try to do, and then define a a reasonable, reasonable sigma algebra. Sorry, reasonable measure on x cross y if x, y are measure spaces. Yep. And we'll see what reasonable means in a minute. So, what we mean by reasonable here is we would hope that the Lebesgue measure on the product, right? So, so we, so reasonable here means we hope that the theory allows the Lebesgue measure, the Lebesgue measure on Rn to decompose into the Lebesgue measure on Rk and Rn minus k, right? Because this is because Rn is the same as Rk crossed into Rn minus k. Okay. So reasonable just means that so in some sense Rn is higher dimensional than Rk and Rn minus k. And that means that Rk and Rn minus k are lower dimensional, whatever that means. Um, so if we decompose Rn into these two things and we do this like iterated integral, which is this thing over here, we would hope that the integrals give us the same thing, right? And moreover, the Lebesgue measure applied in the product sense is this exact same thing as the Lebesgue measure applied on in the normal sense. What we can then do is we can decompose Rn as R cross blah 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 n times Okay, so we get a bunch of integrals in one dimensions. And why do we like one-dimensional integrals? Well, in the case of continuous functions and in the case of smooth functions and whatnot, the Lebesgue integral and the Riemann integral, they agree. Okay? So, moreover, in the general case of if a function is Riemann integral, then the Lebesgue integral and the Riemann integral are the same. And we have a lot of strong theorems regarding the Riemann integral. For example, the fundamental theorem of calculus, right? So we know how to evaluate integrals in one dimension. Um, so okay, let's start off with defining a suitable sigma algebra on X cross R. So um, let us take X sigma X and Y sigma Y. Then note, okay, so our question is like, what would a reasonable element of the sigma algebra be? And if you remember from topology, right, the reasonable thing would be if you want to take the product of two spaces, you take as the basis of your topology, um, the finite products, right? So that's exactly what we're gonna do here. Then we define the sigma algebra, um, sigma x, sigma y. This tensor product symbol is different from the tensor we looked at in linear algebra. Um, we will talk about why we use the tensor in just a second and not the cross. We define the sigma algebra this to be the smallest sigma algebra generated by so A times B, where A is in sigma Z and B is in sigma Y. So this is the exact same thing we did in topology, right? Where we defined the product topology on a finite product of topological spaces to be generated by the sets that were products of two things. And so if we draw things out, so for example, A was a set that looked like this, B was a set that looked like this, then A times B would be this over here. Okay. So that's why so uh we call A times B a rectangle. Again, it doesn't actually have to be a rectangle. For example, if you had a circle and then you crossed it with this, so this is an R2, this is an R, the resulting object you get is a cylinder, but we'll still call it a rectangle. Um, okay. Are there any questions?
No.
Okay. Okay. And now here I use this symbol. This symbol is pretty arbitrary. The reason we don't want to write something like this is because an element in here would be of the form A comma B, right? Where A is in sigma X and B is in sigma Y. B is in sigma Y, which is not the type of this set over here is not so A times B is not sorry AB is not a subset of X times Y. So that's why we avoid using the Cartesian product. Okay. Okay, so now we'll just define some things. So again, if we look here, if I fix a value here, I can look at this line, right? Um, I can look at everything above it. And this gives me a cross section of A times B. Right? So I fix a value of X and I look at everything above that. Um, and as we saw, we wanted to integrate also like this, right? We fix a value and integrate up, and then we integrate along, right? So So this is a useful sort of no, notion. So we define, so let E be a set, let E be a subset of X times Y, then the cross section, um, the cross section of E over X in X is defined as, so I'll write it as this set over here, like this. Okay. Um, and then what it's going to be is it's going to be the set X comma Y where X is fixed and Y is runs over E. Um, so it's going to be like this. Okay. So you fix X and then you look at everything so that XY is in E. And then similarly for Y is defined as, so I'll write it like this, XY in. So the important thing to note here is in this one, X is fixed, and in this one, Y is fixed. Okay. So just don't let the notation confuse you. Okay. Um, okay. So as we introduced the topics today, we saw that we would like to integrate functions over cross sections. But to do that, we would also need the notion of a cross section of a function, right? Um, and so we can reasonably talk about the cross section of a function. So let f be from x cross y into I don't know, whatever. Um, I don't know, it doesn't really matter. A. Okay. Um, then the cross section uh of f over x in x is defined as, okay, so f, and then I restrict it to x, it takes in y, and it just gives me f of xy. Similarly, for y is defined as, I mean, it's the exact same thing. Okay. Now, an important thing to know, like one important thing we could ask is, okay, if we take a measurable function, um, if we take a measurable function in x um, cross y, and then we ask ourselves, okay, are the cross sections measurable? Because if they're not, that's already like this already doesn't work, right? Um, because this cross section, for example, is a function on y. So fx is a function on y. So we can talk about whether this thing is measurable or not, right? So we would really hope that this construction that we've done so far makes cross sections makes cross sections measurable. And it turns out that because we've done this very similar, because we've taken topology as our guide, right? And if you have a continuous function in a product space, the um the individual functions that make up the the projection functions have to be continuous. And the analogous statement is that it has to be measurable. So yeah, if A here was the extended reals, um, so if f x cross y into R is measurable with the exact same proof as in topology, we have um, f x and f. So fx would be measurable, is measurable in y, and fy is measurable in x. Okay, with pretty much the exact same proofs. Okay, does that make sense?
Yeah.
Okay.
Okay.
You can just stop me if I'm either going too quickly or something doesn't make sense.
Okay.
Okay. So, okay, we've talked about measures. We've talked about the sigma algebra. So the next step is we want to define a measure on this space. Um, so let's see how we can go about doing this, right? So suppose we already, um, the way we want to define the measure on the product space is by looking at, we sort of want to build up the measure. Um, we want to build up the measure of x cross y from the measure of x and the measure of y. Like we don't want an entirely randomly new um, measure, right? Um, so let x sigma x and mu and y sigma y eta, let's say nu be measure spaces. And now the question is, how can I define a measure on x cross y? How can we define a measure on um, x x cross y sigma x sigma y, right? And the way we're going to do this is a little it's a little different. So the way we're going to do this is we know that we're building up the theory of product measures so that decompose um, we can decompose an integral over like lower dimensional and um, quotes, right? So we're gonna define the measure in such a way that sets this up. Okay. So what do I mean? What do I mean by this, right? Also, I just want to mention that here we're going to work with sigma finite measures. Um, and the reason we want to work with sigma finite measures will become apparent um, like near the end, because like some of the theorems that we'll discuss will not make sense if the measure is not sigma finite. Um, but again, our main goal is to work with Rn and the Lebesgue measure, and Rn with the Lebesgue measure is sigma finite. So, I mean, those are the sort of spaces we want to look at. Okay. Um, so I'm just gonna define some notation now. So, if f is a function from x into like R, and x is some measure space, um, then we write the integral over x of g d mu is the integral. So the way we write it is like this. So it's just to make sure that we know that we're integrating with respect to which variable or in which space are we integrating. Okay. Um, then what we're gonna do is we're gonna use the fact that um, so now use so now note that if E was some measurable set in X, then the integral of the characteristic function, right? The integral of the characteristic function was nothing but the measure of E. So in some sense, if we imagine that we had the notion of integrals before, then the measure uh, defined on X is just defined to be the integral. Okay. So we're going to use this exact same idea to define the measure on the product space. Okay. Then suppose E was in the product measure. Um, then note first that for all x in X, EX is measurable, right? So the cross sections have to be measurable as we discussed. This What this then means is that the cross section of the characteristic function is also measurable. And the same thing holds for y, right? So if we had the cross sections of y. Um, they would also have to be measurable just given the construction. And each of these are also measurable. And since they're measurable and each cross section is a simple function, right? Because it's either always 0 or 1, these are integrable over the individual spaces. So then what we can do is we can define, so using this, define the measure, okay, the product measure of E to be the integral over x of the integral over y of the characteristic function. Um, and now I'm going to be very loose with this and write it like this. Um, but what this means, right, is that here we're fixing x. So here we're looking at the cross section of x, right? And then we're integrating with respect to the second variable. Okay. So we're what we're doing here is we're treating in this case here, we're treating this as a function of y, right? And this function is now from y into r, right? So we can integrate. So what we're doing is we're integrating. So we're integrating. Another way to look at this is for each x, so we're defining, define g of x to be a function that integrates over y the um the cross section with respect to x of y. Okay. And then now you can check that this is integrable because each characteristic function is integrable. Um, and then you know that each cross section is integrable, so the whole thing has to be integrable. And then what you're doing is you're taking the product to just be the integral over x of g of x, d mu of x. This definition is a little confusing, so if there is any question, please let me know. Yeah, so are there any questions?
No question from me.
Okay.
Yeah.
Are you following though? Like, is everything I've said so far making sense?
I have like a intuition of what's happening. So I
Yeah, I
think,
mean, the idea is that like because we're building up to integrating like on each line, right?
yes.
And then we want to add up all these integrals. Because we want
Yes.
to build up our theory like that, we're defining the product measure so that it sort of gives us it gives you the iterated integral as part of the definition rather than as a corollary.
Okay.
Right? So it's like it's quite literally we're defining the product measure so that it's like this. So it works with iterated.
Oh, okay.
Okay.
Oh, yeah. Thank you.
And
Thank you.
if this is not making that much sense, that is completely okay. Um, Next meeting we will like talk about the specific case of R3. We'll
Mhm.
spend majority of next meeting on R3. Um, and that's because a lot of the theorems that we'll use that we'll try to generalize in the case of like manifolds will come from R3. So it's very
Oh,
important that we sort of, get used to working with R3. Um, Also, there are
okay.
some questions on the problem sheet that I think will be useful to just do this iterated integral action.
Mhm.
Okay. Um, so now we can sort of make sense of what iterated integrals mean, right? So uh so so then we can define the iterated integral of f from x cross y into r um, as so the integral x integral y fx y d y d mu x is just defined to be the integral of over x of the integral of y of the cross section of x, like the x cross section, and then that function integrated with respect to x. And now you could have asked me, okay, why did we decide to integrate with respect to x first and then y and not y? Sorry, why did we integrate with respect to y first and then x and not x then y? Um, we'll see that in the case for measurable functions, sorry, in the case of like characteristic functions, um, it doesn't actually make a difference. Okay. So in the case of characteristic functions, it will not make a difference. But then all the theory that we have is built up on characteristic functions, so we can just adjust as we go. Like because the measure of a set is just defined as the integral of this characteristic function, um, like the measure is well defined. So um, we could we could have also defined um, mu e as the integral over y, integral over x of c but we will see that, oh, sorry, that it doesn't matter. It will not matter. So for now, we'll leave the question of like, why did we define it one way and not the other for, later. Okay, so let's actually do an example. Um, let's actually do an example to sort of see what's going on here because this is a lot, right? So okay, let's look at the integral over the unit intervals of the same function we talked about above, right? D mu, sorry, call it lambda y d lambda x. This is why we introduced like the variable we're integrating with respect to, because if I just wrote d lambda, that would be very confusing. Okay, so now we know that this function is Riemann integrable. So we can just apply the fundamental theorem of calculus. And what we do is we first keep x fixed. So x is a constant. Um, right? We x is a constant. Since x is a constant, and we can just use the fundamental theorem of algebra, we can very clearly see that this integral evaluates to x squared plus 1/4. Okay. And then finally we have to integrate with respect to x. And then you can see that this would be 1/4 equals 7/12. Okay. Now let's do this calculation with the integrals flipped. Okay. So what do I mean by that? I mean, we first integrate with respect to x and then we integrate with respect to y. Um, there's no reason we should expect that we get the exact same answer. Okay. Because we would be integrating genuinely new functions. Yeah, do you have a question?
No,
Okay.
it's okay. Yeah.
Yeah, so yeah, let's just swap the order of integrals. So let's integrate x squared plus y cubed d lambda x, and then let's integrate with respect to y. Doing this first integral, we keep y as a constant. Um, so what you're left with is 1/3 plus y cubed after applying the fundamental theorem of calculus. And then you do the fundamental theorem of calculus again, and what you end up with is the exact same thing. Okay. This is looking promising, right? This is looking good. Um, so we would now hope, right? We would now hope. Hope is a very strong word here because we really, really need it. Um, we would now hope that the integral over the square of this function um, would be 7/12, right? Because that's sort of what it's looking like. It would be, right? Um, do you agree with that? Like, do you agree that the integral should be 7/12?
Yeah, I see why it is.
Yeah, because each iterated integral was the same. So
Yes.
we
Yeah.
would really hope that it is. So
Mhm.
this actually leads us to three important questions. Okay. So so we have three main questions. The first one is this is this even a measure? Right? Is this even a measure? Because we haven't really checked that. We haven't checked that it is a measure. And we have no reason to like expect it to be a measure. Um, it is not entirely too difficult to check that it is in fact a measure. Um, if you recall the definition of a measure, um, we need it that it's firstly non-negative. And that's very clear to see because this function is either 1 or minus 1. Sorry, is either 0 or 1. So this integral is at least 0. And since this integral is at least 0, this integral is at least 0. So okay. Next, we have to check that if we have a disjoint union of um, measurable sets, the measure of their union is the sum of their measures. If we have a countably infinite disjoint union. Um, but then that just uses like facts about the like single integral, which we did talk about. So it follows that yes, this is a measure, and we're happy that it is a measure. Yay. The next question that we obviously have is, does the Lebesgue measure, does the Lebesgue measure, or is the Lebesgue measure on Rn a product measure of R of the Lebesgue measure on Rk? Why do we keep writing 4? Rk and Rn minus k, right? Because that's what we were hoping, right? That the Lebesgue measure is sort of, you can build up the Lebesgue measure in two different ways. One is you look at the sigma Borel set or the sigma Borel algebra, and then you extend the sigma Borel algebra. But that's decidedly very complicated, even in one dimension, right? Like even in R, that's already very hard to do. There are there are very there are some Lebesgue measurable sets that are extremely disgusting to work with, right? So the Lebesgue measurable sets are already not very nice. Um, so you could work with it that way, but again, that's not really the best way to work with the Lebesgue measure. The other way that we were hoping is that the Lebesgue measure from the sigma Borel extension would be the exact same as the Lebesgue measure that we build up just from products of R. Because doing the analysis for r is significantly easier than doing the analysis for r squared or r cubed and so on. So if you, for example, took r squared, you could look at r times r, which is r squared, and then you would hope that the Lebesgue measure sort of agrees with both of them. Um, and it turns out that it does. Okay. So yes, um, it is um, a product measure of uh, the Lebesgue measures. And this sort of should be expected because if you look at the Lebesgue measurable sets that we have in Rn, of course, like higher dimensional cubes are measurable, right? Um, and those are nothing but a product of each of the sides, right? So, so rectangles, like the product rectangles that we defined above, they're measurable. Um, so you sort of have at least that they intersect, right? And now you can then do a little bit of trickery and show that like open balls are measurable. Just because you can like fit rectangles in, you can fit like a bunch of rectangles, a countable union of disjoint rectangles. Um, but we know each of the rectangles are integrable, sorry, measurable. Then the disjoint union has to be measurable. And so, okay, since open balls are measurable, we know we at least have that the product measure contains all the Lebesgue measurable sets, right? Because the Lebesgue measure on Rn is the smallest measure, sorry, is the smallest sigma algebra that contains um, the open balls. So if you have a measurable space that contains the open balls, it must also contain the Lebesgue measurable sets. So now our only thing to show is that the Lebesgue measurable sets are precisely the product measurable sets. Um, and then you can do the same thing because now the rectangles are measurable, and then the product measure was defined to be the smallest um, the smallest sigma algebra that contains all the rectangles. So then it contains the Lebesgue measure. So the it contains the Lebesgue measurable sets. Okay. So that's sort of the idea, right? You sort of so yeah, you can see it's not very hard to convince yourself, at least, that the Lebesgue measure arises as a product um, of the Lebesgue measures on the lower dimensional spaces. Um, this again, this notion is quite quintessential to how we will do multivariable integration in Rn. So does this make sense?
Yeah.
Um, okay. So now we come to the third question. Okay. And the third question will be the most important, well, the second most important after question two and question one in terms of computation is the integral um, over the product measure equal to the iterated integrals, equal to the iterated integrals. Okay. This one is a very subtle question because I mean, it's very obvious to see that if the product measure were to be the same as the iterated integrals have to be the same. Okay. So that's one condition we need. Okay. Very easily. Um, we can already say, okay, if the iterated integrals are not the same, then the integral over the product can't be like does not even exist. And we'll see an example of this actually, where the iterated integrals both exist, but the um, the integral over the rectangle doesn't. Okay, so let's actually now answer this question. Okay, So the answer to this question is actually wrapped up in two very important theorems that we will make use of extensively. And the first theorem is called Tonelli's theorem. So what is Tonelli's theorem? So suppose um, that x sigma x mu and y sigma y nu are measure spaces. Again, sigma finite measure spaces. Suppose also that we have f from the product into the extended reals um, is non-negative. Because remember, this is how we also defined the integral, right? We first integrated non-negative functions, and then we extended to the case of like any function. But you can, get away by saying that it's non-negative almost everywhere. Because again, we don't care about measure zero sets. And is also sigma x is it's measurable in the product measure. Now, what we do is then we consider if we go up here, the way we defined the iterated integrals was first by defining this function on x, right? That integrated over one of the slices and then integrated that function. So we're going to look at both the slice functions. So we're going to consider g of x equals the integral from y. I'll be a little sloppy here and I'll just write it like this. But you can take this to mean, the whatever. It, it's that's not too important, but yeah. Because again, it's just notation. And h of y to be the integral over x of f of x y d mu x. Okay. What happens now is both of these are measurable. Um, G and H are both measurable in their respective spaces. Okay. Um, and the integral over the product, right, with the measure we defined, mu cross nu, is equal to the iterated integrals. So here we integrate f d nu y d mu x, and this also equals the integral over y, then the integral over x of f of x y d mu x d nu y. Okay, so Tonelli's theorem says that, okay, the way we've constructed the product measure is precisely the way we would want to, integrate, because now this makes calculations very simple, as we saw with this example over here, right? Um, this function is non-negative, so Tonelli's theorem says that, okay, firstly, this iterated integral and this is an iterated integral should have agreed. Moreover, what Tonelli's theorem is saying is that this is actually true. Okay, this is true. So yay, very good. With, with
That's
the
where it comes from.
huh?
Is that why, like, that's the verification?
Yeah, so we don't need to compute the integral over the rectangle. Instead, we computed this much simpler integral,
Oh,
right?
right.
By just
Yeah.
by just making one of the variables constant, right?
Mhm.
By making one of the variables constant and then integrating, because we know how to do that by fundamental theorem of calculus,
Right.
right? This is what like Calc 2 is, right? Um,
Yes.
is just you just treat one of the variables as the integrating variable and everything else is constant. So Tonelli's theorem is saying that if you have a non-negative function, you can just you can just treat each variable separately, basically, and
Yeah.
then integrate.
Right.
Um, so let's do an example that's slightly more complicated, I guess, in the sense that it combines the functions because here like x squared y cubed are sort of like they're different, right? Um, they're not really intermingling. So let's say we wanted to integrate x y. Okay. I have no I If I wanted to integrate this the way that we did before, um, I would somehow have to find a sequence of um, I would have to find a sequence of like simple functions that approximate this function from below, which I don't know how to do. So what Tonelli's theorem is saying is that I can integrate over, let's say I want to integrate over x first. Um, so it's saying that I can integrate over x first and then integrate that over y. Okay. But now, since this is just a single variable integral, I can just use fundamental theorem of calculus. So what do I get? I get x squared, x squared y over 2 from 0 to 1. But this just evaluates to y over 2. Oh, sorry, y over 2. And now this is just y cubed over 6 from 0 to 1, which is just 1/6. Okay. So we went from an integral we have no idea how to do because we'd have to approximate it with simple functions. We use Tonelli's theorem because this is non-negative. It's continuous everywhere, so it's measurable. Um, and it's measurable on this set because it's continuous on this set. Um, and yeah, the integral is very easy to compute. So do you see the strength of Tonelli's theorem?
Yes. Yes.
Okay. But now, okay, this is we also want to integrate functions that are like not always positive. Um, so we can just extend. Turns out the extension works, and this is called Fubini's theorem. So theorem two is Fubini's theorem, and what this says is that suppose x sigma x x sigma x mu and y sigma y nu are sigma finite measure spaces. Um, suppose f from x cross y into R is measurable, is measurable. Um, you usually, I guess, write the measure here, but I wrote the sigma algebra. I'm not sure why. Let me just change that. Okay, measurable. But now we need an extra condition. Because if you remember, when we defined the integral of non-negative functions, when we defined the integral with respect to any function, we required that the positive and negative part, at least one of the positive and negative parts had finite integral, right? Because otherwise you'd land into situations like infinity minus infinity, and then you don't really know how to deal with that.
Yeah.
So we impose the condition that the integral of this guy is finite. Okay. Then um, so then we get two things. So one, we get that the integral over y of f of x y with respect to y is finite for for almost every x. Um, this just means that the set of points where this fails to be finite is measure 0 in x. And we also have the same thing for y. Yep. And then we have the exact same conclusions. We have the exact same things as above. So let me just copy this and let me just paste it because I don't want to rewrite all that. Okay. So
Yeah.
so Fubini's theorem, the Fubini's theorem is what we were looking for, right? As we saw with this example, Tonelli's theorem made the integral over the rectangle very simple. Um, and yeah. Now, one question that's a little annoying, I think, is this condition in Fubini's theorem. Um, it turns out actually that this is a very important condition, um, as well, as we will see now, actually. Hmm. So this example that I'm going to show comes from like Axler's measure theory book. Um, so
Is it the linear algebra one?
no, it's the measure theory one.
Oh, yeah. Is it the same guy?
Yeah, yeah, it's the same guy.
Okay.
Um, I'm pretty sure that book is also open source. So, um, a lot of the stuff in the measure theory sections that we've actually talked about, like, is taken from this book, from that book.
Mm,
Um, I've explained things in a different order. Um, like for example, all this that we've talked about over here, like all this stuff is basically chapter 5, I want to say, of that book. Um, but the way we did measure, like, so a lot of the things are from that book. Um, so yeah, I guess I should actually give credit to that book.
mm.
Um, yeah, so a lot, if you want, you can also like read that book.
What
It's
is the
it's a very
name?
nice book. So
Okay, I'll search it up real quick.
yeah, so the way he does the way he does the things in that book is he first does the single variable. So he defines the Lebesgue measure over R. And then in chapter 6 or something, he defines the Lebesgue measure and Rn as the product measure. But the way we've defined the Lebesgue measure is first, in general, and then we're like we're using that as a as motivation for whether our thing actually, you know.
Mhm. Hey, also, I noticed, I think in multivariable calculus, there's also like a Fubini theorem. Is it related or
This
not?
is yeah, so yeah, the Fubini theorem is a more general theorem than the multivariable Fubini theorem, but if you see,
Oh,
it's the exact same statement.
oh, okay. Yeah.
It just means that you can swap the order of integration.
Mm,
Um, have you guys started integration in 2 3?
no, it's next semester, I think.
Oh, it's next semester. Okay.
Yeah, I've just heard of this name, I think.
Okay.
Yeah.
You'll be very ahead because the I'm planning on actually giving um the details of the exercise. So we're going to look at one example that comes from the exercises of measure theory, like the measure theory book by Axler. Um, I'll leave the computations. Uh, I'll like give that as an exercise in one of the problem sheets,
Okay.
and it's not it's not too hard if you know how to do partial fraction decomposition. Uh,
Oh, yeah.
okay, so the example is as follows. So consider f from this into R by f of xy is x squared minus y squared over x squared plus y squared all squared. Okay. Then the integral over 0, 1 of the integral over because I've defined this, I'm not gonna keep putting brackets. I think you understand what I mean. Um, of f of xy with respect to y and then with respect to x is equal to pi over 4. But the integral, or but if we swap the integrals, we actually get negative pi over 4.
Mm.
Okay. Um, so the exercise in the book asks you to say why does this not um, violate Fubini's theorem? Um, and the reason for that is very simple, actually. So if you look at the positive part of f, is defined to be x squared minus y squared over x squared plus y squared when x is bigger than y and else. And the negative part um, is defined as the negative of this. All right. But now notice that the denominator here, right, is on has like x to the 4. Okay. So you're integrating something as x to the 2 over x to the 4 from 0 to 1, right?
Mhm.
So like each of the both of so the integral um of this and the integral um diverges, right? They're both infinite.
Mhm.
Um, and because of this, it ruins this condition over here. Because if you write out this definition, this is the positive part of f plus the negative part of f, right? So you need that this integral and this integral are both, well, at least one of them is not infinite. Um, and then you can check here that both these integrals actually are infinite. Um,
Mhm.
so the integral is not finite. So we see that, okay, in Fubini's theorem, it is very important that this condition actually exists.
Mhm.
Yeah, so if you want a more in-depth of whatever we've talked about today, you can look into Axler's book.
Oh,
I think it's very good. Um, if we go to the previous meeting, um, um, for this one, I've taken inspiration from a bunch of different places, but it's not I don't follow like word for word um, any one thing.
mhm.
But this one, it's more sort of more like word to word. Again, I've explained things in a different order because the way we introduced things was completely different. But yeah, um, I will um, I will. Are there any questions?
No.
Okay, so um, I'll end the recording and then I'll just like tell you about what we'll do like next class.